Before we start, some announcements on the next lecture. Actually, we're going to have the CICS seminar because the speaker couldn't come on Monday. So if you show up on Thursday and you see lots of strangers, just keep in mind they're strangers to me as well because I would have never seen them before. But because of the particular talk, they will show up, okay? So that's not a reason to hide because there's going to be a big crowd, okay? So the talk is going to be, don't remember the exact title, about uncertainty quantification in some applications related to fluid dynamics. But the theme obviously will be very general, so it will be very much related at least to the subjects of this class. All right. We haven't really finished with the hidden Markov models. There's way too much stuff to do, but I decided to just take a break and move a little bit forward to cover state space models to be sure that we don't stay behind. And if there is time, we're going to come back to cover, basically to remind you that all these message passing algorithms we did, they give you the same results for the alpha and beta messages as we covered them in the last two lectures. And also I wanted to give you generalizations of HMM, which are very practical, lots of applications. And I don't know if any of you is doing any project in that area, but somehow I know every student loves to do very complicated projects, and they don't like the simple things because in the simple things you can find the truth. In the complicated things you're lost. All right, so I like simple things, right? I can see a smile there. So I like simple projects. And every time, even for undergraduates, my whole life I say, I want something trivial for dummies. No, people want to design bridges that vibrate because it looks good, right? Correct? Are you designing any bridge? Any high-rising building? No? All right. Okay, so we're going to discuss about state space models today as an introduction. This is part sort of this general theme of using probabilistic graphical models for data-oriented problems. And this concept is so fundamental, basically. You know, maybe your problem has nothing to do with state space models, but you can transform it in a way that you can utilize some of these algorithms. And I'm going to show you a trivial example of doing Bayesian inference to find the posterior of some parameters with no dynamics, and we can mimic these things we are going to learn today to do Bayesian inference. You can even do weird things. You can do time integration of ODEs using state space models. And actually, that's a very interesting area, even of current research. All right, so the slides are not done yet, but actually the HMM slides that hopefully you got from by email, I'm almost 3 slides left to check them, 3 slides, okay? I don't want to post them because every time I look, there's another mistake I have to correct, okay? So there are 3 slides, and I will post this and the missing lectures very soon. So these state space models lectures are almost done, so if not post it, I will send you an email with them. All right. So HMM versus SSM, basically the graphical model is identical. We have an evolving state Z, so that's our dynamical system, and then we have some noisy observations that they're Y. The only difference from HMM is in the HMM model, like similar to a Gaussian mixed model, these Z variables were discrete. Here the Z variables are continuous. That's the only difference. Okay? So in addition, to make things a little bit more interesting, we have sort of introduced in both the dynamical and the observation model some input variable U that you can think of it being some forcing term that you prescribe. All right? If that term is not there, there is nothing that it falls back to the previous models we had. So the general SSM model, we have the dynamics described by this equation in a very general form. We're going to simplify, of course, so that this is some easy function to work with. So use the input zt minus 1, the state of t minus 1, and some noise. And the observations basically also has a u-term. It depends only on z at that same time t, and has its own noise as well. So really, so this is identical to what we did with HMM. Actually, in HMM, we said you can put as an observation anything you want to, and we did the case, for example, with a Gaussian model. But right now, this can be a Gaussian, and this can be a Gaussian. All right. Okay. So if you remember, I defined sort of a number of problems that they are standard in the context of data simulation, and those problems are identical for SSM. Okay. So what's the name we gave to estimating this? How do we call this distribution? What's the name we gave to that? And it's universal name. I mean, you need to know this because it comes everywhere. So what name do we call, how do we call this distribution? It's a posterior of the state, right? But we gave a name, we call it something. In the literature, you will see it with a name. What's the name? It's not the name of Newton, it's just a name that defines in words what this distribution is about. So what was it? Exactly. It's the filtering distribution. All right? So this distribution is known as the filtering distribution. Okay? We discussed about the smoothing distribution. I think I'm going to come back to it. So in the smoothing distribution, it's basically the estimation of zt, but instead of using data up to time t, you have all the data up to the end capital T. Okay? So this is the filtering distribution. And of course, this is the predictive distribution where you don't really care about z, all right, like in lots of problems, but you want to know what's the probability of your next measurement if you already have data up to time t. Right? So there is all of the problems we did for HMM are basically the same problems in any data simulation case, okay? If it is HMM, SSM, or anything else, the same sort of problems are of interest. Okay, the most standard problem, all right, and maybe any students from electrical engineering, maybe you guys have taken a course on linear filtering or something. Is there any course on linear systems? There is something? Kalman filtering, is anybody teaching those? All right. So, so we're going to spend very little time to discuss this, at least today. The good news, right, is that all of these equations that are implied by the Kalman filtering for linear systems, you can actually derive them with belief propagation. And in the case of belief propagation, you can derive all of the equations for all the filtering, smoothing distributions, everything you're interested, even if the dynamics are non-linear, even if the observation model is non-Gaussian. So you can do anything you want to, okay? But today, we're going to be very elementary, with a little bit, of course, a probabilistic graphical taste, to discuss a linear Gaussian model. Now, it's linear because you notice the evolution of the dynamics is linear, so these matrices A and B, they're functions of time, but they don't depend on the state Z. We will actually discuss this after spring break on how we're going to extend this when A and B are functions of Z. The observation model, again, is linear, and the noise is Gaussian. You can estimate, right? I mean, you can just looking at this equation, if the noise that drives this is Gaussian, then for all good chances, all distributions of interest will be Gaussian. All right? Now, you can assume that and actually force a methodology to give you the mean and the variance of the different distributions and say, oh, that's the filtering distribution, that's the smoothing distribution, but it would be nicer if you actually, do some algebra to show that the distributions of interest are Gaussian. Now, in some problems, these matrices don't have a subscript t, which means they don't depend on the index t, or time, let's say. So in this case, this linear Gaussian model is a stationary problem. All right, some notation. maybe I need to add this explicitly in the slides. When we write distributions, and as we said today in the lecture, everything is going to be Gaussian, we're going to use to describe means and variances two subscripts. The first one will refer to what time we do the estimation of the state. So in this case, you know, this is time t. And the second index will refer to the time scale where we have data. So in this case, it's from time 1 to t. All right? So for example, if this little t was a capital T, that would be the smoothing distribution. You see that? All right? So the notation, the indices here are very important. If the indices change, this values for this mu and sigma are completely different. Again, the first t is the estimation time. We estimate here the posterior of gt. The second t is the time that up to which we have collection of data. In this case, 1 to little t. Okay. So obviously for this linear system, the problem is known as the Kalman filtering problem, but that's of secondary importance to our lecture today. So let's do some trivial examples. I mean, literally, you can find books on the subjects, you know, and if you look on books on, I don't know, probabilistic robotics or something, the whole subject area is about SSM, basically. Okay? So this is an example of object tracking. So let's say you're tracking a missile, and you're interested on a state that is defined basically by the location of the missile. This is sort of a missile moving on a plane. A rather stupid problem in the notation here, but Z1T and Z2T you can think being X and Y location, and Z dot 1 and Z dot 2 being the speeds in the X and Y direction. Okay? You're really interested to compute all of this independently, because, you know, if you calculate somehow, let's say, the velocities, and then you try to do integration on this, you're not going to get very accurate results, right? Because then you're going to have to worry about error of integration or differentiation, depending what variables you take on z. So here z is both the location and the speed of the object. That's what we need to track. So the dynamical problem looks like this, okay? And I'm going to give you explicitly so you can convince yourselves that there's nothing really complicated. So again, Z1, let's forget that t. Z1 is the X location, this is the Y location. So if you look at the first equation, this times this plus this noise, it says that the X location is the X location of the previous time plus delta, which is the time step, you can think of integration, times the velocity at the previous time. This is like an explicit time integration scheme, okay? And then you have some Gaussian noise. And in the context of the velocities, you don't do anything. You say this velocity is the previous velocity plus some noise, okay? And the observations, again, it's a linear model like that, so let's see exactly what the observations look like. So let's say you're observing the location of the missile. So you basically want from this z vector to extract z12 and z2t. So you basically have 1, 1, and the rest is 0, plus some noise, okay? Obviously, I forgot when I said that everything is Gaussian, right? You have to start with a distribution of the state also that is Gaussian. Because, you know, if I put for a probability of Z1 to be some weird distribution, then good luck. Nothing is going to come to be Gaussian, okay? So in this case, P of Z1 is Gaussian. And again, notice the notation. What does 1, 0 means here and 1, 0? Why there is a 0 there in this expression based on our notation? So that's the prior. So what's the previous? This is what we start with. What's the prior? What's the previous? Nothing. All right, so there's a 0 there, okay? And if you assume basically that you don't really have any information for the location of the missile to start with, right? Before you collect any data, you can assume that this is sort of an infinite, if you like, variance. So basically the result can be anywhere in the plane. So just to give you some sort of trivial results, and again, you may want to go, before actually Shuvik gives you this as a homework and you guys have to extract this and program it, you may want to actually run this trivial example from Murphy's toolbox. Will take you exactly 5 seconds to look at the program and see how in 5 lines you can actually implement the equations we will discuss today. But so the problem is basically figuring out the path of a missile. You have some noisy observations, which are these green circles, all right? This is the true path. So it's more or less, in a state path for y equal to 10. But you try to estimate this from these noisy measurements. So these little crosses you see are basically the results of this filtering distribution, okay? So it looks noisy actually if you look, it goes up and down, etc. This is way more smooth there. So, and obviously you notice when you start, because you don't have any data, you rely on the prior, basically the first step, you're a little bit away from, well, this is where it's supposed to be, but it picks up quite fast, okay? So this is the filtering distribution. So if you assume that the data come one at a time, you can update the state where the missile is, and this is what you see this crosses there. If you do smoothing, actually you get very nice results. So this is a zoom-in picture of the smoothing, and you can, there is no oscillations basically in the results. They look pretty good, okay? So that's why we call this smoothing. You are basically stabilizing the problem by using not only current data but future observations as well. So this is the smoothing distribution. All right. So let me discuss about this robotic slump problem. It's a standard problem, and there's a whole book actually on the subject area for those interested. Again, if I ask, is anybody doing any projects on this, I know the answer is no. So let me define the project for you. So let me put these things all up. Well, actually, let me use this picture. I'm going to go backwards, okay? So assume you have a robot that is moving, all right? It does whatever tasks you have assigned to do, but it tries to identify at what location is at each time, and we denote this location as X, okay? So if you put, let's say, a robot to clean this carpet here, right, and starts navigating, you have to put some markings and say, there's a wall there, Shuvik is there, don't go close, there's a student there, etc. You need to give some markings. So these markings are these capital L's, okay? So literally, that's how these little robots that cut the grass work, right? You provide some markers in your yard, and the robot basically learns where it is and where it needs to go to navigate through the space. So this landmarks, capital L, L1, L2, they're of fixed location, okay? And you provide them. So the robot is trying to estimate where it is at each time by measuring its distance from these fixed landmarks. So basically, the robot doesn't know where it is, right? But when it sees a landmark, it's sure I'm 1 meter to the left of this. So in this case, for example, at time 1, it sees landmark 1 and landmark, let's say, 2. On time 2, it sees only L2. On time 3, L1, etc. Okay? So the location is estimated using those cells. Now, the observations, all right, y1, y2 are these distances from the landmarks, okay? And notice something. So I marked here the observations to indicate that this is evidence. Notice something, that L1 and L2 are not conditionally independent given the evidence. Can you see that? So even though the landmarks are fixed, right, they're not conditionally independent given the evidence. And can you, it says there, don't read this, so let me cover it, all right? Let me put my body here, all right? So why L1 and L2 are not well, you can read it there, you can read it there, so I don't help very much. Why L1 and L2 are not independent given the Y's? Use the biggest ball algorithm and look at this probabilistic graphical model and tell me what makes L1 and L2 dependent with the biggest ball algorithm. To prove conditional independence, what is the biggest ball tells you we need to do? Take the ball and following some rules, see if there is a path connecting L1 to L2. So do we have a path connecting L1 and L2? Why? Why it's not blocked there? Huh? The V, that is the explainer way situation, right? We have two causes, all right, that explain this, all right? So actually, given this, L1 and X1 are independent, okay? So effectively, the ball can go through here, can go through there, can reach there. So this makes this problem slightly more complicated. So given Y, these L's are not conditionally independent. Actually, and we're not going to do this unless someone decides or has submitted a project on this. A nice algorithm to actually handle this and use linear Gaussian systems is to write the probability of the posteriors, let's say, of L, not only given Y, but assuming that you are given X as well. So then they become independent, and you can use ideas from Kalman filtering and sort of particle filter methods to come up with a very easy solution of this. Okay? I mean, this sounds sort of like a trivial problem, right, to handle, but in the context of robotics that work on warehouses, you know, Amazon.com, you know, where they take books from shelves here and find the next book and they navigate, not hitting each other. You know, this is algorithms that basically are trivial, were implemented maybe 10, 15 years ago, and those who did implement those became very rich, okay? And that includes one of my very young colleagues a few years ago, who sold basically his one-man company to Amazon, okay? So you can, these are very simple algorithms, but simple things pay. Complicated things, they don't pay because they're complicated and you cannot do them right. All right, so the observation model, all right, is the probability of Y given Z, right? This motion model is the probability of X with dynamics, okay? And this is basically this filtering distribution together with the error bars, because this is a two-dimensional problem, right? You get, and the, you know, this filtering distribution is a Gaussian, so basically you can draw an ellipse, all right, around the mean of this filtering distribution, and you notice, so you start from one location where you know where you are, and then the uncertainty actually grows, but then as you come closer to something that you have seen before, the uncertainty is reduced. Now, if you try to go backwards on the same path, because you already, you know, have collected a lot of data, this is the smoothing problem, this smoothing uncertainties will become way small, right, all the way back to the initial state. The implementation of this algorithm is literally 10 lines, okay? 10 lines. Now, let me just say a complication, right, because this sort of introduces the ideas also of dynamic graphical models that I don't know if we will discuss, you know, before the end of the semester. But so what? So let me go back to this picture. Okay. So you are measuring Y, right, and you try to estimate this else, and the location basically X, where you are basically at every instant. So L and X is your state Z here. The two things together is the state z, and you try to estimate them given y. So when you start, all right, let's say at some locations, you know what, there is, you know, can you tell me how this diagram is going to evolve with time? All right, what do you think is going to happen? You notice when you're at time 1, the landmarks that you see is L1 and L2, so your inference will involve L1 and L2. Then you move somewhere else, the only thing that you see is L2, so your state will involve only L2 down there, it will involve L1, you know, et cetera, et cetera. So what happens as you move? What happens to, so if you think that you build a big correlation matrix that connects all your L's and your X's, what can you tell me about that correlation matrix as you move in time? Is it sort of everything correlates with everything, or something happens as you move in? I mean, you notice here, again, time 1, L1 and L2 are there, time 2, L2 is here, then L1. So what can you tell me about the correlations that you have between, let's say, the L's and the X's, or even the L's themselves as you move with time? Are they changing? You remember what makes L's correlated is the observations that you make. All right, so you observe something that connects two landmarks, right? So the correlation is very high. You move, you don't see a landmark, there is no correlation whatsoever. So you can think of a dynamical graph basically that represents what you see here, where the strength of the correlations moves with the graph. So at each time, some things that were highly correlated become uncorrelated, right? And they're basically insignificant, okay? So, so this basically falls in the category of a system that is evolving with time, so a graph that is evolving with time. So if you want to read more about this, I recommend basically to read this book on probabilistic slump. So there is a reference somewhere in the notes that discusses further on this topic. All right. And so you can see, you know, this is sort of a snapshot of the correlation metrics that you get for the filtering distribution. You can see there's lots of zeros there, all right? It's extremely sparse, so whatever algorithm you implement needs to account for the sparsity on the correlation metrics. All right. And obviously the people who became rich with this concept, and actually that's the book I was referring to. Let me go back, all right? So this is the book. For those interested, you can actually download the whole PDF for free directly from the author's website. Okay. All right, so let me convince you, before we discuss anything in detail, why the state space models are sort of very powerful, and you should make use of them, even if there is nothing that has anything to do with dynamics and evolutions of state and noisy observations or any of these things. So let's consider a Bayesian inference problem where it doesn't matter what it is, but you try to estimate, given some data, the posterior of some parameter theta in your model. Okay? Can be anything. Okay? There is no dynamics here. Nothing. Okay? So what I'm going to do is, the way you do in Bayesian things, you're going to put some prior model. All right? So here's my prior. And of course, we have some observations. And we're going to try somehow to address this problem with state space sort of thinking. Now, to do a state space thinking, you have to pretend that there is dynamics in the problem. And so what I'm going to do is, I am going to pretend that indeed there is a dynamical evolution of the parameters theta. So I'm going to make theta to have a subscript t, even though there's no t, but you know, I'm going to take this sort of as an iterative process in some index t, and the dynamical problem is going to look like that. The probability of theta t given theta t minus 1 is really a delta function that says theta t should never change. Does that sound reasonable to you, right? I mean, if you try to do a Bayesian inference and you want to estimate parameters theta, yeah, I mean, you can waste your time and assume that this is a dynamical problem where the parameters never change. Right? It's an overkill. It's like, you know, again, you may say I'm wasting my time. All right, yeah, let's see what that waste of time, if it pays off, okay? Now, what I'm going to show you now, right, if you take the sigma 0 to be infinity, the estimation for the parameters, we're going to get only a point estimate here, right? I'm not going to calculate the whole posterior. We're going to get a point estimate of the parameters theta, but if this sigma 0 is basically infinitely broad covariance matrix, effectively, we're going to get a maximum likelihood estimate from this approach. Okay? Otherwise, we're going to go directly and get a nice mark estimate. All right. I haven't really done the solution to the linear system of equations, right? So I'm giving you this sort of as a demonstration of what is coming. So when I tell you that equation is correct, you have to believe me. This is what's going to come in. Okay? So we're going to cover today in the lecture the exact Kalman filtering equations and how we compute the filtering distribution, so the posterior of z given data from 1 to t, the filtering distribution, etc. But I want to assume that I know somehow those equations, and I want to know what are they going to do for me on this Bayesian inference problem in updating the parameters theta and see if some magic comes out of it. So I remind you that, what slide was that? Let me just, you remember the linear observation model was that yt is equal to ct times zt plus, there was no u here, plus some Gaussian noise with this variance. You remember there was a symmetry. Okay, so, all right, so, so this is the observation model basically, all right? So the observation model, y is a Gaussian, okay? And because this noise is Gaussian, the mean is c times z, all right, c times z, and the variance is sigma squared. And so let me sort of try to help you here to see what I'm trying to do, okay? I will assume, right, so I will limit it to a very specific case, but actually can be very general here. Think that somehow theta are some parameters in a regression model, right? So I'm doing sort of supervised learning, okay? So think that somehow in the supervised learning problem, you give your input xt and you compute your output yt. That's your data, right? You give xt and you know yt, and then you want sort of to compute the parameters in some linear regression problems that will allow you to compute y for any x. So we can be very specific, okay? So think, again, so if you want to compute the observation model will depend on what the input is. And so the C matrix that I take here is X transpose, all right? So X transpose theta, you know what it reminds you? Think of a regression model that is basically, theta transpose X. Y equal theta transpose X. Usually when you write regression models, you think of Y equal W transpose X plus some noise. So my W is theta here. All right? So the point is here, right, that Y in the linear Gaussian, in the linear SSM model is C times Z plus some Gaussian noise, all right? So I am taking Z, the state, this is weird now, I'm taking the state to be the parameters theta, but I make them dynamic. This is what I don't know, all right? My C matrix is X transpose, is my X coordinates, let's say, because I'm doing supervised learning, okay? So theta in this, let's say, Slump are my regression coefficients, okay, in a linear regression model. So, and I'm doing this, let's say, when the input is it's not 1D, it's a multi-dimensional problem, so I write X transpose times theta plus noise sigma squared. So this is my observation model, basically. Okay? So if I know the input, this response depends on the state, and the state is theta. All right. So I am going, so pretending now that the problem is dynamic, all right, and this theta t has evolved dynamics, somebody can write down, all right, somebody can write down the filtering distribution for the state z, and the state z are the parameters theta. So in other ways, if you go and provide regression data x1, y1, x2, y2, xt, yt, there's really any time, but let's say you provide t data points for your regression thing, I can write down the mean of the filtering distribution, which is analytically known, and we will derive it today. So that mean comes to be basically the mean at the previous time, and remember time here is dummy, all right, times A transpose. What is A transpose in my problem? You remember, so A comes in the evolution of a dynamical problem, like zt equal A times zt minus 1, but really my dynamical problem is a delta function. All right? So, so A here basically is like an identity, okay? So mu t times, so if I know the mean at the previous time, and I know this matrix that is called the Kalman gain matrix that we will derive today, and I'm going to give you an exact expression shortly, I can write the updated mean with this expression. Now, when you look at it, it looks very weird. For our particular problem, it comes that this Kalman gain matrix is analytically given by this nice expression. Okay? So, sigma t is what? So in the filtering distribution here that I have, right? So sigma t will be the covariance matrix, okay? Will be the covariance matrix, and I'm not listing what it is, all right? Actually, let me be more correct because I realized here we forgot an index. So this should be sigma t given data up to t, okay? And I'm not going to write explicitly because it doesn't really matter what it is. So I am going to take this equation that we will derive today, and I'm going to write it for the update of the unknown parameters, and this is the form that it takes. And I want you to look not on the details of the symbols there, but on the functional form of this equation, and tell me everything that somehow you are reminded. All right? Tell me, so what is this actually, when I look at this in the context of a regression problem? What is that? So, you know, let's say we have trained the problem with data up to time t minus 1. So I use all my data up to t minus 1, and I did, and, you know, hierarchical, if you like, every time I go and update the parameters. So this is the best parameters I have up to time t minus 1. So what is yt minus xt transpose theta t minus 1? Yeah, that's the residual, that's the error that you do with the model that you have calibrated up to time t minus 1, okay? So, for those who have taken courses in machine learning or, you know, the statistics, computation statistics course in the fall, right? This is sort of a standard term when you do supervised or unsupervised learning one data point at a time. It's this error that drives the updates. So notice what it says here. Use the previous parameters to update, plus something times the error that you do at that instant, okay? Now, does this, so, okay, I do know this comes in everywhere in machine learning. What else, what other buzzwords this thing reminds you? What other algorithm of online learning that you should know up and down because it's sort of the standard update formula? Any names? Most probably, it never came in the lecture in this course, but in the fall and any other machine learning course. Feedback. Maybe not. What is this equation looking like? Does it remind you anything at all in the context of anything else? Come on, Mr. Nick, what is reminding you this? N and R. You mean R and M maybe? R and M, you know, wow, that's a miracle of nature. Yes, you're not implying the Robbins-Monroe algorithm. Yes, all right, thank you. The Robbins-Monroe algorithm, okay? But I'm actually surprised that you are thinking of the Robbins-Monroe algorithm and you don't think updates of parameters that say neural networks or anything else. Any online algorithm has this form. Anything. Any online algorithm has exactly this form, okay? The point here is, right, when you do Bayesian regression, you want to find, let's say, point estimate of the parameters, you take all the data, you show the least squares problem, regularized, etc., and you say that's my map estimate, etc. Here what we do, by making this problem dynamical, we compute this online, one data point at a time, okay? And we start with some parameters, and then we update them based on this error, okay? Now, usually when you do online learning with Robbins-Monroe algorithm or, you know, any sort of idea of stochastic gradient descent, usually what you have here is some coefficient that is the learning rate for your problem. And usually because that learning rate is sort of arbitrary, you have to go a few times through all your data sets to get this to converge, okay? Now, it happens because here this comes to be exact. If you go once through all the data, you get actually the exact estimate for a linear, for this problem. Okay? So basically here, the learning rate is not arbitrary, but is given precisely. So if you put the correct information for sigma and sigma square, and you go through all the data set once, then you will converge to the exact answer. But depending on what you use for prior, it would be either your MLE or your map estimate. So the point here is, right, you need to imagine things, and if you imagine that somehow you can transform something to a dynamic problem, you get interesting algorithms. You get an online learning for map estimation or MLE estimation that brings you back sort of to standard ideas of machine learning where the error drives the updates in the parameters. Now, so this is what I was saying basically before, right? But if you substitute this with some generic rate that you sort of select with practical training, you know, just you try different values, this is what is called the least mean squares algorithm, all right? So this you have to iterate once or twice to the data sets to make it to converge. The algorithm that I just discussed is called the recursive least squares algorithm, and basically it converges to the exact solution once you go through all your data sets. So this is an interesting thing, and by the way, if you search the literature, and again, I know you would not because these are the easy problems. So for these easy problems, you can use these ideas to do some very interesting things. Even, you know, as I said, you can even take deterministic ODEs and somehow transform the problem to dynamical problems and use these ideas to do time integration. You can do whatever you want, basically, okay? So, and again, these formulas will be derived today. They are analytical for the general Gaussian linear dynamical system. All right, we don't need this. Okay, so this is basically the setup for, let's say if you have a linear regression in one dimension, right? So this is your observation model, all right? The parameters theta are basically W0 and W1, and so this is theta, and the way I think that we do is we assume that theta changes with time, but time really is not time, it's an iteration, it's a dumb index to allow us to come up with a nice recursive least squares algorithm, okay? Very nice idea, and again, you want to implement this, the code is already there, it's 10 lines, right? You can look at it, all right? And play with it as well. Okay, so let me, before we go to the common filter thing, give you some other things that somehow they don't look like state space models. So for example, if you try to do predictions on the stock prices, right? So you follow the particular stock, you know, what the value on Wall Street was every day, and you want to do a prediction what the price may be tomorrow based on historical data, right? So you want to find, let's say, the y at t plus 1 if you know the date of time 1 and t. So in this case, there is no z, there is no latent variables. So even if you don't have latent variables, you can assume that somehow your data are generated by some strange hidden variables, right, that capture the dynamics of the problem, that capture this they represent accurately this evolution of the observations that you have. But since you don't care about this, it's not a big deal, because at the end of the day, since these models come to be Gaussian linear models, you can integrate Z out completely. So basically, I don't need to have Z there. So Z is used because it can give me sort of correlations in my Y's, right, that they're long or short range as I desire, right? But since I'm only interested in Y, I can just go to do this prediction, to predict this, I can integrate my Z's out. So, point here is, you may not have any Z's, but introducing them in your model may assist you actually to get this distribution, all right? So don't have something that says, oh, but I don't have any latent variables. Well, it's up to you to make them latent variables, because how do you represent the dynamics? And a good way to represent the dynamics in your system is with one or two or multiple chains of latent variables. So consider that to be an approach. So let me give you some simple models. So this basically the observation models is this local level A that you see here, and what you do is you introduce some dynamics on this local level. Okay, so y is equal to at plus some Gaussian noise, and at minus 1 plus another Gaussian noise. Okay, so the probabilistic graphical model for this is basically y depends only on at, but you assign some dynamics on at that in this case they are Markovian, so at depends only on at minus 1. Okay, so you can see actually what interesting data you can generate with this, right, and why these ideas are very powerful when you play with data. So for this local level model that you see here, you can actually try completely different scenarios. You can have a system that has noisy observations but has deterministic dynamics. You can take a system that has noisy dynamics but deterministic observations. And then you can make everything noisy, and you can see how by playing a little bit with the parameters, the results can look day and night. Okay? So, and again, you can write, I mean, you can, this code again is a few lines to do these predictions. So this is, something that you will use in econometrics, predicting earthquakes, so I can sound like civil engineer, right? And things like that. Modeling the wind speed, right? That must be relevant as well. Okay. All right. And so here is a sort of a little bit more complicated graphical model where the observations y depend on this local level A, but this local level A depends on B that has its own dynamics, okay? And if you do actually this, you can control even the slope, if you like, in your observations. So for example, if you think of this model as it is now, right, and take that there's no evolving dynamics here, so bt minus 1 equal to bt, so every time you calculate AT, you'll be adding a constant amount of B. So at time 1 you have B, at time 2, 2B, 3B, 4B. So this B is going to come to be sort of the trend, the slope in the evolution of your observations. So you will have sort of some linear trend plus noise around it, okay? So this can allow you to very easily to actually model, whatever behaviors you like of dynamical data, and you see here, again, the three cases where you play as to what is deterministic and noisy, if it's the observations, the system, or both, okay? All right, so let me, I'm going to finish because this is the most important problem both in the context of statistical and machine learning modeling, but also it comes everywhere in physics. This is what's called the ARMA model, the autoregressive moving average model. You may have seen it in a completely different context. So the x at time t, okay? There's no here observations in z, right? I'm just writing this model like that, and it's up to you to interpret it as to what is the state, what you observe, and things like that. So xt here depends on this p previous values of xt, xt minus 1 to xt minus p, but also depends on these parameters w, that you can interpret them as hidden variables, so from 1 to q. And you can actually, with this thing, you can model, I mean, why do you do this modeling? Because you try to sort of control how the x's correlate, in time, let's say. Do you have short-length correlations, do you have long-term correlations, or you have both? And so this ARMA, this autoregressive moving average model allows you to do that. So, for example, I'm taking the case here when q is equal to 0, so this term is not there. And take a trivial case of p equal to 1. Immediately you can see that this is the autoregressive model 1. So for p equal to 1 is your first order Markov chain, right? So one of the things we learned about Markov chains a few weeks ago, basically you can model them with this ARMA model. Now, if you take the p to be equal to, this term not to be there, and you only have this q there, basically the dependencies for q equal to 1, they look like that. All right? So somehow now you introduce correlations between the x's because they come from this common cause. So x1, x2 depend on w1, x2, x3 from w2. So here you have short-range correlations. Okay? So, and again, this is only for q equal to 1. And if you use q equal to 1 and p equal to 1, you can get a probabilistic graphical model that looks like this. So it comes as basically correlations in time that are both Markovian, for example, you can see here from x2 depends on x1, but also there are these connections through w that you get extra sort of nature of correlations on this model. This is a huge area of research. If your work has anything to do with dynamic data, then this is a subject area on its own. People do PhD thesis actually on this topic. Okay, so don't consider sort of because this looks simple are only for a lecture. All right, simple things. You know what it means? They're applicable everywhere, and if they're applicable everywhere, their impact is enormous, and everybody cares about what you do. Okay. If you work only on the winds, wind engineering, then basically, as they say, as the song says, is going with the wind, right? Okay, so here it is, it's a little bit more complicated than that. Okay. All right, so let's say we have 23 minutes, so we have about 20 minutes to, I really need to cover the Kalman filtering because sort of a little bit off out of the course, but we need basically to see the equations and convince you in the next lecture that you can actually get the same equations with message passing in graphs. Okay. So here's the problem. We want to compute the filtering distribution of zt. It's the posterior of zt given my data for time t, and giving this input vector u from 1 to t. Okay? So my notation that I'm going to use, here there is no reason to put mu t slash t because everything is t. So when you have two subscripts that they're the same, I am using basically this mu t and sigma t. I want you to remember the notation because the equations may get a little bit more complicated. Okay? So remember the notation we use, what mu t and sigma t is for this filtering distribution, this posterior of zt given my observations. Okay. In machine learning, right, everything that has to do with linear algebra and Gaussian models, okay, involves a bunch of very fundamental equations that maybe you guys have not seen. The students last semester got tired of using these equations. They thought the course was too hard on them. But these are the equations that have nothing to do with statistics. If you do machine learning, these equations come everywhere. So what are those equations? For if you have a Gaussian P of x with this linear variance, and you have another condition of variance of y given x, which has a mean that is linear in x, right? This is what we call a linear Gaussian model. Then you can actually use Bayes' rule to invert this, and from the probability of y given x and P of x, you can get the probability of x given y. All right? And you don't need to prove this. The proof is in, Bishop has a nice proof, you know, in my notes from last semester, you can visit them. Murphy's book, any machine learning book, on their first chapter or second, has these equations, okay? So if you want to compute probability of x given y, you basically have to form the joint from these two, okay? And then from the joint, basically go back and find the posterior of x given y, okay? So it comes to be like this, all right? So I'm going to use these equations about 10 times today. And also what, if you can, from these two, if you multiply them and you form the joint of x and y, actually what you can do, you can integrate x out and basically close the square in y and come up with a Gaussian distribution to describe P of y, so that Gaussian distribution is actually given by this nice simple formula. So when you play with Gaussians, look if the problem is a Gaussian linear. If you have something that the mean is a linear function of x and the distribution of x is Gaussian, then you know everything else is Gaussian. And these are the formulas that can take you from y given x to x given y, and can take you from P of x to P of y. All right? So these formulas, I'm going to use this extensively, and the next formula that I'm going to use is something we have used it infinitely times, and it's used infinite times in machine learning. Every time you have to invert big matrices, you need to think if there is some sort of factorization or a way to rewrite the matrices in this form, so you can use what's called the Woodbury lemma or this matrix inversion lemma, okay? And I am not going to go into the details, but here you notice this inverse matrix can be written as like that. So if it happens that this B matrix, if this matrix here is n by n, where n is much less than this n by n matrix, obviously this pays off computationally. And a lot of times you don't see this result, but if you try to do, let's say, Gaussian processes, you will immediately, you know, if you don't use this, you'll be inverting a million by a million matrices rather than 100 by 100, okay? So the Woodbury lemma, it is always there. So when it's something like that, it screams at you and says, use me. Okay, matrix inversion lemma. Okay? All right. So, to compute this filtering distribution, it's easy in the sense that we have to do exactly the same identical steps we did for the filtering distribution for the hidden Markov model. So you remember in the hidden Markov model, to get the filtering distribution, the first thing we have to do is to get the one step ahead prediction for z, all right? So given data up to time t minus 1, all right, the first step we will do is we will compute the predicted distribution of zt. And here notice that I don't use u from 1 to t minus 1, because if I'm going to do prediction of zt, I'm going to use the input that I have, which goes from 1 to t. Used given. It's like a forcing term, okay? It's an extra term that I'm using there. It's a forcing term. So we know u, obviously, we're going to use it. So the derivation that you see here, it's exactly the same as for hidden Markov models. So effectively what has happened is you can think you plug in here a zt minus 1, and then you integrate in zt minus 1. And then what you do is you use Bayes' rule to write this as this probability times this probability. And this is very easy because this model here, you know what it is? This is your dynamical model, right? What is this distribution? It's a Gaussian defined by this A and B matrices. And what is this? All right? This is the probability of the state at t-1 given the data up to t-1. I actually don't give the u from 1 to t because I'm referring here to t-1, so this would be u1 t-1 really. So, you remember we said we're going to denote the mean and the variance with the one subscript only. So these are the mean and the variance at time t-1. So recursively, I'm going to assume that I know this distribution, and I'm going to try to get, eventually this is what we try to get, right? We try to get this, right? This is our notation. So obviously this will be this distribution. Yes? We will do it recursively. We will assume you know this, and then we will compute this distribution, and using this distribution, we will try to find the filtering distribution of ZT given data from 1 to t as a second step. All right. The equations don't mean anything unless you have a sense from where they come and how you actually do the algebra. So if you look at the equations, algebra is important, but it's important to know, yeah, I can do this because it reminds me of this problem. So look at this now. We want to integrate in zt minus 1 of something, a distribution of zt that has a mean that is a linear function of zt minus 1 plus a Gaussian of zt minus 1. And what do we need to do? We need to compute the marginal of this that will involve only the state zt. Does that remind you of any formula? Does this remind you of any formula whatsoever? A linear Gaussian model, and this is function only, prior p of x, and we need to compute the marginal. Right? It says, use me, Gaussian linear model, So the results are important, okay? You look at the previous formulas 2 slides ago, and you say, you know what? This distribution will have this mean. I'm just copying the formulas with the correct symbols. The correct symbols means this linear matrix is A, there's a B there, there's a mu t minus 1, sigma t minus 1. So this is the answer. And I denote the mean and the variance here with 2 indices to remind me that this is the predictive at time t, but I only have data up to t minus 1. You remember, we don't use the 2 indices if both times are the same, basically. Okay? But here, this is the predictive distribution having data up to t minus 1, and this is the predictive at time t. Again, have done nothing but copy the formulas for linear Gaussian systems that I showed you before. So this, one step ahead, prediction of ZT given my data to t minus 1 is a Gaussian with this mean and the variance, nicely. So how do we compute now the probability? How do we compute actually the filtering distribution, right? So if I have data from 1 to t, how do I compute the posterior of ZT? Basically Bayes' rule, okay? So I split my evidence from 1 to t to evidence from 1 to t minus 1, and I put yt separately, and then I write this proportional, the term of the denominators are important. I write this as yt given zt, so that's my observation model. And what distribution is this? It's a Gaussian that has a mean mu t minus 1 and a covariance sigma t minus 1. Now, I am looking at this model, and without showing you the equations, can you tell me if you can actually compute analytically now this product, and why, based on these linear Gaussian models? In other ways, if I go back to 3 slides, can you tell me what is there that immediately says, yes, I can do this? So can you tell me what is this distribution of yt given zt? Give me some symbols. I mean, what is yt as a function of zt from our Gaussian linear model for SSM on the first line? Yt was the matrix C, let's say, ct times zt plus d times ut, which we don't care, plus noise, a Gaussian noise. So, do we know what this distribution is? Yeah, I mean, we basically, this model here, all right, is a Gaussian, okay? and we know exactly what the mean, what the variance is, everything, okay? How about this distribution? Can you tell me what can you tell me about this distribution? Well, it's here. All right? So this distribution is basically another Gaussian. Okay? So let me just write them down. Okay? So this we know. This we computed on the previous slide. And so basically what you have is you have a closed form solution to this problem that is a little bit complicated. All right? So I'm going to show you where the algebra comes. Okay? So this distribution has this mean and this covariance matrix. So the mean is basically the mean of this distribution, all right, plus this matrix K that you will see explicitly in a second, times some residual R, okay, and the sigma T is again defined through this gain matrix K times this matrix that comes here, sigma T, T minus 1. So this matrix, again, you will see in one slide. This derivation, by the way, is not trivial, all right, this product, okay? It takes some algebra, okay? You effectively have the product of two Gaussians, so we're going to have to see how this calculation works. So I'm going to, before I give you the derivation, I want to give you all the symbols. This Kalman gain matrix is given basically by the covariance that we computed on the one step ahead predicted distribution times C transpose times this matrix S inverse, and this matrix S inverse discusses here what it is given by an analytical expression, all right? We know the C matrix. This again comes from the covariance of the Z given the data to T minus 1, and this is the noise in the observation model. So everything is known, right? If this calculation, if these formulas make any sense, what we need to do is take the mean from the one step ahead predicted distribution and correct it using this residual R, all right, multiplied with the Kalman gain matrix, and the residual R is basically the observational time T minus this entity here. And so what is this? This is the mean of what? You remember before when we computed the one step ahead predicted distribution ZT given data 1 to T minus 1. This is not the Z. This is the predicted distribution of the observation given data 1 to T minus 1. But that's an easy distribution because YT is C times ZT plus the input plus some noise. So effectively the mean will be C times, all right, the mean of the predicted one step ahead distribution of Z, which is this, plus dt times ut. I'm not giving you any derivation of this product, right? The only thing I'm telling you is, you told me that this is a Gaussian, which is nice, on ZT, and also, you know, okay, this is a Gaussian, and this is also a linear model in ZT. Now, right, so this is a linear model in ZT, right? This is, you know, so Gaussian times a Gaussian, and somehow with some miracle of manipulations, we should be using the identities that I gave you, we get these nice results. Okay, so the question is, where do we get these results? Let me put everything here. So where do I get this result? I know you do not write the formulas with a linear Gaussian system, so I'm trying now to give you a proof of this Kalman filtering updates for the predicted distribution. Where do I get this result? So here what I have is YT given ZT, all right? Can you tell me, so it's a Gaussian, is the mean of that Gaussian linear in ZT? So this is a Gaussian, right? Is the mean of that Gaussian a linear function of ZT? You remember the linear system yt equals c times ZT plus the input plus some noise, all right? So yes, there is a C matrix there. So this is a Gaussian that has a mean c times the ZT, right, plus the input plus the Gaussian noise, okay? So basically, what you have is, you have a distribution on ZT that we have computed, and you have another Gaussian that is linear in ZT. And what do we want to compute? We want basically to compute the posterior of ZT given all of my yt's data here, right, from 1 to times t. So basically what you need to do is, I don't want to go back to any slides, right? You need to use the Gaussian updates that I gave you before, and it comes out that the covariance matrix inverse, okay, of this matrix is given by this nice formula, and the mean is given by this formula. Trust me, I have not done anything but basically cut and paste the previous formulas with the new symbols that come in the context of the equation on the top, where I plug in what Gaussian I have here and what Gaussian I have there, and then my linear Gaussian update equations look exactly the way that you have there. All right. Now, these two equations that I cut and pasted from the linear Gaussian system, they don't look like the Kalman filtering equations that I showed you in terms of this K matrix. So the question is, where is that Kalman gain matrix comes from? Because it's not there, all right? So obviously these equations will not be very sort of efficient way to program this, because I see inverses here. So if you want to calculate the covariance, means you're going to have to calculate the inverse of this huge matrix here. Okay, so this will not be very good, very smart way to do things. So let's look at different terms. Okay, so I am claiming here that the first equation can actually be inverted in this nice form that you see here. Can you guess, without again seeing that any derivation from where the equation may be coming? Can you guess that somehow, if I take this and I invert it, that sigma t is actually given by this? Does it look visually anything that we have seen like a few slides back? The matrix inversion lemma, the Woodbury identity. Okay? So basically, if you try to invert this, basically you get cut and paste, change of symbols, you get this nice equation here. And if you notice, there is a c t minus 1. So this is the covariance of the predictive one step ahead using data only up to t minus 1. We have computed that. So I can put this outside, and this whole matrix up to ct, this whole matrix there is what we define to be the Kalman gain matrix K. Okay? So Gaussian linear equation manipulation to give us these two equations, and then we can see sigma t. So we get this Kalman update basically directly in terms of sigma t. And I'm going to give you the update now for the mean, because before when, if I can go back, all right, so we wrote this nice update for sigma. Now I have to give you the update for mu to see that deriving the Kalman equation is also a trivial task. Okay, so what is the update for mu? So let me just go back to be sure that we are talking about, okay. So when I wrote down the update for mu from this multiplication here, this is what you get from the linear Gaussian system, right? So we need to manipulate this to get it in a much more tractable form. So I'm going to rewrite this equation that you see here, so I can start working on it. So this equation has two terms, so I'm going to work on each of these two terms separately, okay? So work on the first equation that looks painful, all right? But let's see why it's not bad. So there is a sigma t minus 1 inverse times mu t minus 1. I leave it as this. And for sigma, I use the update in terms of the Kalman gain matrix K that we just derived, okay? So the first term immediately is written in terms of the carbon gain matrix K in a very nice form, very convenient update, okay? Then we need to update this sigma T times C transpose. Where is it? So we need to update the term. And again, sigma T is written by this nice thing times this times YT. And what I have done is now basically, this matrix actually I don't have to do anything. If I take these two things here and I put them inside the inverse, okay, it comes out, you can write this whole term here. There's no Woodbury identity or anything like that. You can write it as this matrix, and this matrix is really the Kalman filter matrix K. So the update for mu T is basically mu T T minus 1 plus this Kalman gain matrix times basically an error message that tells you what's the error between the observation YT and the one step ahead predicted distribution for Y. That's the mean of Y given data to T minus 1. Okay? So, so basically those are the updates, okay? And, so we actually finished with the Kalman filtering equations, right? If you look at books, they may spend 5 chapters on this, but really playing with the Woodbury identity and the Gaussian linear systems equations, the derivation is basically 3 slides, okay? If you do actually this, and we will do this using message passing, it will look painful, the derivation, but interesting is that message passing algorithms can actually extend the Kalman filter to all sorts of distributions, all sorts of dynamics and observation model. So if your likelihood model is noisy, it's non-Gaussian, it's a Poisson distribution,